Hi, I'm Michael, a high school student in the Yin lab at UC Riverside, and I'm working on fabricating photonic crystals with complex and unique spatial configurations.
The building blocks of these photonic structures are iron oxide clusters with crystallites small enough to retain superparamagnetism. When an external magnetic field is applied, the clusters align into chains with periodicity in one dimension. If the center-to-center distance is comparable to wavelengths of visible light, Bragg diffraction can occur in the visible spectrum, giving rise to bright observable color. By changing the magnetic field strength slightly, the periodicity can be controlled and the color of the photonic crystal can be tuned. A more extreme increase in the external magnetic field strength will cause a structural rearrangement from one-dimensional chains to two-dimensional labyrinths. Because there isn't any significant disorder introduced along the length of the individual chains during this process, the entire labyrinth still acts as a photonic crystal. The primary visual difference is that single bright diffraction spots of the chains turn into long colored bands when viewed from the top.
These types of colloidal assemblies could find use in a variety of electronic and photonic devices, but one of the main obstacles in their actual implementation is that it's rather hard to capture these types of structures in their original state. It's pretty easy to look at these under an optical microscope, but any other form of observation becomes rather difficult because of the dynamic nature of the labyrinths. If we so much as remove the magnetic field under the sample, the entire structure will fall apart.
This can be solved with a modified Stober method. By coating the entire labyrinth in a layer of silica, the normally dynamic structure now retains its shape.
The repulsions between individual sheets cause them to wrap around one another for the overall labyrinthine appearance. Because they're magnetically assembled, if we can control the local magnetic field where the labyrinths form, we can dictate the final arrangement of the labyrinth. This is possible with UV-cured polymer templates.
The templates, when surrounded by magnetic materials, act as magnetic holes and modulate the local magnetic field strength. Because the labyrinths are magnetically assembled, their structure will mirror that of the templates, allowing for a much higher degree of control over the shape and size of the labyrinths. The ability to dynamically assemble such complex arrangements from colloidal particles, to manipulate their morphology with patterned substrates, and finally to immobilize their structure for further characterization and implementation make these two-dimensional labyrinths exciting not only for their significance in magnetic self-assembly processes, but also for their potential in new photonic and electronic materials and devices.